All right, so with our previous lecture, we looked at the slope deflection equation. So let's do a recap of it. The recap of the slope deflection equation. Yeah. All right. The deflection method. Let me just add that to it. Okay. And we mentioned that typically when you have a structure, okay, we need to look at its kinematics. So that's supposed to mean movement, right? Okay. So when looking at the kinematics, which is the movement of the structure, we focus on the movement of the joint. Okay. So movement of the joint. All right. And the movement are in two folds, either this translation or rotation, right? And in the translation, we assume X and Y directions, all right, for the translation. Um, Typically for beams, two-dimensional beams, we assume that the movement of the joints will only be in two directions. It's going to be in the Y direction, and then be also have a rotation, right? The the X direction is assumed to be non-existent because we are making the assumption that there's no axial deformation, right? Even though it happens, even though there'll be some bit of elongation and a contraction of the structure, we usually neglect that because it is very small as compared to the downward movement of the structure. All right. Um, so here, if you have a simply supported beam, all right, we when discussing or describing joints of a structure or a structural member, we assume that the joint can be what's the name? Either support. So this can be joint, or the joint can be where uh, members connect, right? So this could also be a joint right here. And also usually if there's any change in the cross section, that change, that point of change also becomes a joint. So we have discussed that before. All right, so the support can also be joints. So are these supports or are these joints? What are the kinematics of this particular joint, right? So with a simple supported beam, we know that if you have to draw the deflected shape, this is how, oops, this is how it looks like. All right. So there will be rotation in both. So there will be theta A and then be theta B. So these rotations or these displacements are pretty much what you call the degree of freedom, right? We have degree of freedom for three-dimensional space and also for a 2D space. Okay. Um, Depending on which one we are looking at, will determine um, which one works for us. All right. So we looked at um, from our lecture 2, we try, I think lecture 2, we looked at the joints and all of that. So we know the joint system and everything. All right. So pretty much they form our degrees of freedom or our unknowns, all right, or our kinematics, right? So this particular beam is indeterminate in terms of the kinematics. It is indeterminate to the second degree. It means that there are two DOs that we need to find. All right. So we need to find theta A and find theta B. All right. With the slope deflection equation or with the slope deflection method, the goal is to find support reactions. All right. But to find support reactions, we first have to find the unknown displacement. Okay, so we find the unknown displacement, then use that information to now find the reactions. Okay. Or maybe to break it down, use that to find what we call the end moment, typically the end internal moment. And then from there, we use that to find the reactions. All right. So that's how come it's called the displacement method. The reason is because we first formulate our equations in the displacement with the general goal of first finding displacement. Okay. So if you have again a beam, let me use this again, whereby there are end moments. All right. We assume that all our end moments are initially clockwise. So we have this end moment. Let's say this is end moment AB, end moment BA. All right. And then you have some loading on the beam, some arbitrary load on the system. Um, all right, some arbitrary load on the system. What we need to do is that we, so let's say maybe there's a W, there's also some P's over here that we don't know. And let's generalize the entire behavior of the beam. Let's say that, okay, support B also is able to have some vertical displacement or some settlement. So this settlement here is delta, which means that support B is now somewhere here. All right, so it means that your new position of your beam is this position. So let's say it also undergoes some elastic deformation. All right. So this same beam would have some rotation at the end. If this is the straight line between A and the new position of B, is what you call the chord. And then this is the elastic curve. Okay. So you will see that if you are to draw the angle to the horizontal, you'll find the theta A, and then find, so then maybe this becomes your, oops, this becomes your theta A, and then here we have our theta B in a way. All right. Okay. So here the unknowns are theta A, theta B, and delta. Okay. So pretty much what you are looking at is like we've taken a portion out of a longer structure. So I could have, let's say, some structure. It doesn't matter what it looks like. All right. So let me call this maybe O, A, B, C, and D. So I'm looking at here, this portion, right? So definitely, anytime you cut your beam into two, or if you cut your beam into whatever, anytime you cut at these points, you introduce unknown, what's the name? Unknown moments, unknown support reactions, unknown X and Y, stuff like that, right? Yeah. So these moments, anytime you cut your beam, the moment you find, so let's say if you cut it, maybe this is XX. If you cut your beam into XX, you have these moments, right? So these moments here are unknown. Okay? And we need to find them, right? So these are the internal moments. Okay? And that's what I have here as MAB and then MBA. Okay? So we write the slope deflection, the displacement theta A, theta B, and then delta in terms of these end moments, MAB and MBA, and as many as we can have. All right. So once we have that, the angle the chord makes with the initial position of the beam, this angle here is called psi, P-S-I, psi. All right. What else do we need? The delta here is supposed to be our relative displacement. So the video explains comprehensively what the relative displacement is all about, right? So we have our sign conventions and then whatnot. With the sign conventions, we assume that all moments, if clockwise, are positive. All right. The same with rotations. All rotations, when clockwise, is positive. And then we have a few more here and there, right? So based on this arrangement, we are able to write the equation here that MAB is 2EI over L theta A, I'm sorry, 2 theta A plus theta B minus 3 psi plus what you call the fixed end moment. Okay. Then MBA will be 2EI over L 2 theta B plus theta A minus 3 psi plus the fixed end moment at the BA or at the end on the right side. These are the or this is what we call the slope deflection equations. Okay. In a much more concise approach, I could call this end here the near end, and then call this end over here the far end. So instead of AB, to generalize it, I can just say NF. It becomes 2EI over L 2 theta N plus theta F minus 3 psi plus the fixed end moment NF. All right, so near and far. And you can also write the same thing for the far end as well, where it becomes FN, MFN, stuff like that. Okay. So the general idea is to take these equations, use the principle of equilibrium, what's the name? Mema force deflection or displacement relations, and also use the uh, compatibility conditions and formulate equations which we can use to solve the structure. Okay. So first thing we have to identify, always identify the DOFs, right? We don't know what they are, so identify them, like whether there'll be any DOFs or not. Then based on that, you find what you call your fixed end moments. All right. They also determine your equilibrium equations. Okay. And typically you're looking at equations at joints. Okay. Where joints are. And then based on that, you can also write your slope deflection equations. And then together with the equilibrium equations, you are able to determine the displacement or the deflections. Okay. And you find your end moment. Then find support reactions. Then also draw the diagrams. Okay. um from here on, from the end moment to the drawing a diagram side, these three steps are very similar to the three moment equation method. All right. So in your lecture video, you would, I mean, there was an elaborate example that broke everything down on how to solve these types of structures. I'll go ahead, solve one more. And then if you have any questions at any point during the lecture, you can stop me and then we can look at it. All right. Um, Again, when it comes to drawing bending moment diagrams, I can post this maybe later. When it comes to drawing bending moment diagrams, again, we've discussed this extensively last semester when looking at three moment equation method. There are a variety of school of thoughts in drawing the bending moment diagram, and um, I mentioned that we can go with any of them. I mean, there are easier ones that works with for us. Um, yeah, so let's look at what works. Again, for whatever reason, I think we are still struggling with our Benjamin diagrams. And the TA has been doing a very good work with the first years in terms of um, tutorials. If you are interested, you're allowed to join that class, or you can see the TA for further explanations, okay? Because at this point, I think we should be able to draw simple Benjamin diagrams. Okay. So let's try to come up with an example that can work for all of us. Uh, okay, let me just do this. Just making sure that we have the same example. Just give me a second. I want to repeat. This is 50.96, and this is what 81. But they look very similar, so there's no point. Okay, so let's solve an example. Um, so let's say we have this particular structure, hopefully. All right. So something like this. Then there's a UDL on top, and then there's a point load here. So 60 kilonewtons. And then here it's 40 kilonewtons per meter, A, B, and C. All right. The dimensions would be, this is 6 meters. And then here we have 1 meter each. All right. So the goal is that what, I mean, find support reactions, typical questions. Then we draw shear force and bending moment diagrams. Okay, so these are the questions. So again, this question, you can use different methods to solve them, right? Here's an example that you can easily use the trigonometric equation method to solve it. You can use the slope deflection, you can use the moment distribution, you can use the force method, you can use the matrix stiffness method. So there are quite a number of methods out there which you can use to solve this particular problem. All right. So first one, identify the DOFs. All right. So pretty much identify our degrees of freedom, so our unknowns in terms of the displacement. So we have what theta B and theta C. I wish I could solve another example, not this one. Let me see. It's fine. All right, let's just go ahead and solve this one. Just try to um, kill two birds with one stone. How is this going to work? Okay, so let me change the question slightly so that I don't have to. I can do a little bit more than what I'm doing right now. Okay, I so don't want to create my own question anyways, because I have to calculate everything by hand. Okay, let me just go ahead. Okay, let's say support B displaces by, let's say, 30 millimeters. All right. So what this simply means is that when you look at your structure in reality, this is how it will end up looking like. So this is the initial position of the beams, and then this goes down this way. Okay, so this is A, B, and C. So support B displaces by 30 millimeters. So support A is here, support C is down here, and then support B has displaced. All right. Here we know what our displacement is. That is 30 millimeters. So we know what it is. All right. So once we identify our DOFs, which are to theta B and then theta C, our first point would be to what's the word I'm looking for? Find a fixed end moment. All right. So in your um fixed end moment, sorry. In your online, you'll see that there's you have a PDF that says that fixed end moments. All right. So that gives you a table of how to calculate fixed end moments. So if you take span AB, okay, so your fixed end moment, you assume that all ends are fixed for now. That's what you're moving with. Then you have your UDL on it. Okay. So if this is 40 kilonewtons per meter, then we need to find these are fixed ends. So in your notes, do I have it over here? Let me just see if I could bring it up. Just give me a second. We continue folder. Okay, I think I found it. Let me just upload it here. 258. It's okay, untitled. Okay, hopefully it shouldn't take too long to load. Should be somewhere here. Okay, so I'm guessing you can now see my screen. So these are the fixed end moments. Okay, so there are two sets of fixed end moments. The one on the left and then the one on the right. Okay, so the one on the right is a modified version of the one on the left. Okay, modified version of the left. Let me make it simple. All right. Well, I'll explain why it's modified later. But for now, what we are focusing on is the one on the left. So there's actually a longer, yeah. So the one on the left, what we are focusing on. And with a fixed end moment, as the equation states, we assume that the ends are fixed, right? We don't really care about anything else. And then we come in here and look at which of these would satisfy our problem. And in this case, with span AB, this is our, oops, with span AB, this is our fixed end moment for span AB. As you can see, we have the UDL on the entire span AB, and then these values here, WL over 12, sorry, WL squared over 12 and WL squared over 12 are the fixed end moment. There's something very interesting, which I tried and see if I could explain a bit. Where are you? So please, at this point, this is your time to ask questions. If you have any questions, you can always tell the TAs. You can ask, you can chat, whatever it is. Just let me know. Blah, 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 stuff like that, okay? Okay. So me rather spending time here. Let me go to what we're looking at. Yeah, so this is a fixed end moment, okay? Great to have it over here. My W is 40. My L in this case, oops. The L in this case would be the length of the span, which is 6 meters. All right. So the fixed end moment at AB, which is on the left, so that's joint A, for my AB, will be equal to 40 times what 6 squared over 12. So that would give us what to be our answer. So that'll give us did I change my question? Hopefully not. I think I did. So I might need a bit of help going forward. So this is what 120 kilonewton meter. And then your fixed end moment, BA, is also the same thing because they both have the same equations. Okay, nothing has changed. And so this will also give us 120 kilonewton meter. Okay, great. So that's your first fixed end moment. Now let's look at span. So this is span AB. And let's look at span, try to use black. And let's look at span BC. So with span BC, we have again, so this is our fixed end. Then there's a load right at the center, which is what? 60 kilonewtons. Okay. Again, we go to, this is BC. We go to our fixed end moment table and see which one works for us, pretty much, right? And you will see that our fixed end moment would look exactly like in a few seconds. Right. So it looks just like this gentleman on the right. So it means that our fixed end moment BC will be PL over 8, where P is 60. L is the entire length of the span. For whatever reason, you guys sometimes assume that the L is supposed to be half the length of the span, which is wrong. So take note, L is the entire length of the span. So that'll be 2 meters. So P times 2 over 8. And then that should give us, those for the fast fingers, um, that'll give us what, where's my calculator? So 60 times 2 divided by 8. So we get 15 kilonewton meter. Okay. The same way the fixed end moment for CB will be equal to the same 15 kilonewton meter. Okay. So let me put something interesting here. Now look at the directions of the moments. Right. So for the FMAB, it is what? Anti-clockwise. And then for the FMBA, it's clockwise. The FMB is also anti-clockwise. Then the FEMCB is clockwise. This will come in handy going forward. Okay. So once we find a fixed end moment, we write the equilibrium equations. Oops. So we read the equilibrium equations. Pretty much we have 3 joints, right? Um, the key thing is that of course oops, the most important joint to us is joint B. Okay. Joint B is the most important joint to us. So our joint B, if I'm to redraw, sorry, I'm to redraw my structure again. All right. Let me put this over here. It's fine. So our joint A, I have this. So this is MAB, MBA, MBC, and MCB. So this is MCB, MBC, MBA, MAB. The way we label them is that M is the moment that subscript A and B, whether B or AB, they define the span you are looking at. All right. And then which letter comes first determines which end of the span you are looking at. Okay, so that's basically what we are trying to work our way around. I think I have a question, but I didn't see that early. Yeah, so FMBC will be negative, which is correct. I know there's no Jennifer in the class, but somebody's is called um, Jennifer today. All right, so let's move on. So now we know our joint. It means that this joint here, joint B, is the most important. Oops, joint B is very important to us here, which means that MBA plus MBC should be equal to 0. Now, another interesting fact, which I think we should all realize, that this is what a hinge supports, right? So this is a hinge support, right? And a hinge support at the end. So hinge, let's say end supports, right? If you have a hinge or a ruler, sorry, hinge or it's the same thing. That is a hinge or ruler, and it's a support at the end. It means that the moment at that point is what? 0. So, I mean, this is from statics. So it means that our MCB is also equal to 0. That much we can define. Okay. So once we know all of these, now I don't know what's wrong with my screen. So now we write the slope deflection equations. Okay. So you formulate equations based on MAB, based on MBA, based on MBC, based on MCB, right? Generally, we know that M and F is equal to 2E I over L 2 theta n plus theta f minus 3 psi plus FEM NF. Please, the psi is equal to delta over L. All right, it's just comparing the chord to the length over the deflections that would occur. Okay, so let's look at MAB. So MAB, before I do that, let me, okay, because there's going to be deflection. Let me have a ruler here. Okay, so usually I wouldn't draw it this way. This way is not the best. It's not the best. Just take note. I don't want to cancel, but this way is not the best. The best would have been this. Let me try and see if I can figure it out. Okay. So I actually had should have been a different color. Or is it okay. So this way. Let me take the rest of go away. So my support, this is actually my support B. This is my support A. This is my support C. So this is A, B, and C. All right. So this is actually the better way to draw it so that this is my MAB. Here is my MBA. Those don't really change. This is my MBC. And here is my MCB. So there is some deflection here. Let me draw it outside. Okay, so this is delta, that is 30 millimeters or 0.003 meters. Okay, I'm hoping my zeros are enough. Oh, 102 minutes, so 0.03 meters. Okay, this will come in handy. All right. So this is the best way. So this is best way. Okay. All right. So that this will show us it will show us the username, the fact that support B is displacing. All right. I can see any support will display support. A can display support. C can display if there are more, and then I can have like 2, 3 more supports displacing. Okay. Always take note. There are so many ways by which we can analyze these different types of questions. So let's go. MAB. Let's start with the equations. MAB is equal to 2E I didn't give EI value, but let me do that. Um, um, so let's say that EI is constant, right? So that we don't have to worry ourselves. So EI is constant. So it means that in the end they'll cancel out. So it doesn't really matter what values they are. So EI is constant. So MAB is equal to 2EI over 6, 6 being the length of the span AB. All right. Then to bracket 2 theta A here. So 2 theta A plus theta B minus 3 delta. Now, the value of the delta is important to us. Is it negative or is it positive? Okay. And then if you look at the sign conventions, if you take a span, so this is on the side, if you take a span, okay, and then you have the situation, for example, right? So this is A and this is B. This is your delta. If the right side is lower than the left side, which is what we have in this case, then delta is positive. Okay. So the delta will remain positive, so then becomes delta, which we know that to be what? 0.03 over the L, which L is 6, time plus the fixed end moment, FMAB. All right. So let me just put here FEMAB. So this will be simplified into MAB plus 2EI over 6. Theta A is 0, right? This is fixed support, so the rotation over there is 0. So we only have theta B minus 3. This whole thing becomes what? Times 6 times 3 divided by 6. So that'll give us what? This becomes 0.015, okay? Minus. Why minus? Because we are assuming that this is equal to, sorry, not plus. We are assuming that this MAB here is supposed to be what? All the equations leading to MAB are all clockwise. So if they're all clockwise, but my fixed end moment is giving me an anti-clockwise rotation, then it means that 120 anti-clockwise or counterclockwise is the same as what? Minus 120 clockwise. All right, great. So here it becomes minus 120. The screen has a mind of its own today. All right. So we can again simplify all of these. EI is constant, so we can expand. So let's expand. Let us go ahead and expand. Let's get this out of the way. So this will be 1 over 6, 1 over 3, right? So it becomes EI theta B over 6 minus so it becomes minus 0 EI 0.005. I think there are 2 zeros over, and okay, no over. All right. So let me take this guy away because it's blocking my path. Let me put you somewhere here, it's fine. Then minus 120. All right. So this is the equation for MAB. MBA will be the same. My slight differences. So MB is going to be 2EI over 6. 2 theta B minus, sorry, plus theta A minus 3 to bracket 0.03 over 6 plus, in this case, 120 and not, because it's supposed to be plus FMBA, right? So here is FEMBA. Okay. All right. So let's see. So again, we expand this. Theta A goes to 0. All right, because support at A is fixed. Okay. So this will give us, if we are to expand, that will give us, yes, 3, not 6. Let me correct this. So we get 2EI over 3 theta B minus, then we have all of this interesting thing, right? So it becomes EI, to brackets, the same thing, I believe, right? Nothing changes over here, so it becomes minus 0.005 plus 120. Okay, so the major challenge is writing these equations. But again, that is simplified because we have the general term and then we just log things in there and then we go ahead. Okay. We'll do the same for MBC. So MBC is equal to 2EI over the length for member BC is 2 meters. Okay. So we get 2 theta B plus theta C minus 3 over 2. Then minus 15 for the fixed end moment at B. So this is fixed end moment for BC. Now, if you take member BC, this is how member BC now looks, right? With your displacement now this way. So with member BC, this delta now becomes delta is negative. Okay, so in here I'll get minus 0.03 because it's negative. That's the only thing that will change here. And the reason is because you are writing your equations in terms of clockwise being positive. So anything that is anti-clockwise will be negative. Okay. If you look at the rotation of the chord, it goes anti-clockwise for this case, whilst for the upper one, the rotation is clockwise. Okay, so this is positive, this is counterclockwise or anti-clockwise. So it is negative. All right. So I can simplify this to be MBC to be equal to EI 2 theta B plus EI theta C minus this whole thing, 0.03 times 3 over 2. So this give me plus EI 0.045. You can be doing the math on the side just in case I mess up something, then you can prompt me because I'm doing the calculations in real time. Then MCB will be equal to 2EI over 2 theta, 2 theta C plus theta B minus 3 into bracket minus 0.03 all over 2, then plus 15, okay, for the fixed moment. So this is going to be FEMCB. Okay, just take note. So our MCB, when simplified, will be EI theta, EI over 2 theta C plus EI theta B, then plus this whole thing, EI 0.045 plus 15. Okay, so we have our four equations. So this is equation 1, which is this long one, right? This is my equation 2. This is my equation 3. And that here is my equation 4. So let me label them. Equation 1, Equation 2, 3, and 4. All right. Now we know that MBA plus MBC equals 0. All right. All right. So MBA plus MBC equals 0. So it means that simply puts add equations 2 and 3. All right, so let's add them together. So let me be a bit lazy here. That's being lazy is the worst thing that can happen to you. So this part that I've just copied and pasted is supposed to be, oops. It's supposed to be the MBA section. Okay. All right, so let me copy the other parts as well, the MBA part, and then trying to do a bit of because so I've already copied the MBA. What I need is the MBC. All right, let me oops. Okay, so this is sorry, EI 0.0. Okay, so now let's do the MBC. Where are you, MBC? So let's also copy that part of the MBC. Hopefully, yeah. Let's see. I copied more than I was supposed to. Let me just take some of them off. Mhm. And then take it off. All right. So there was an EI, so plus EI theta B plus EI theta C. So we get an interesting equation. So all of this was equal to 0. So then let's sum that like terms. So we have this one here. We have this also over here. So if we sum these two together, 2 over 3 plus 1 will be 4 over 3, right? No, 5 over 3, sorry. 2 over 3. Yeah, 5 over 3. So we get 5. So 0 is equal to 5 over 3 EI theta B. Then we have plus EI theta C. All right. Then we can also add the other these two terms. Let me color them, these two guys together. All right. So it becomes minus 0.005 plus 0.055. That'll be 0.04, right? Yeah. So plus EI 0.04. Okay. Then plus 120 minus 15, that'll be 105. So this becomes one of our equations. I would say the first one of our equations. So once we have this as one of our equations, the next thing will be what's the word I'm looking for? So we have this as one of our equations. The next one is a look at our MCB, right? We also mentioned that our MCB is equal to 0, right? So we have already established that, which means that I can rewrite this as 0 is equal to, again, just copy the whole thing here. So yeah, MCB is equal to this. So now we have two equations to deal with. We have two equations. So let me call this equation 5 and equation 6. So we can say that solve 5 and 6 simultaneously. Okay, so let me do some one or two changes to it. All right. To make things easier, let's assume that EI let's say E is equal to 200 GPA. So let me create something for the I as well, and let's move on from there. So let's see what the value of I could be off the top of my head. Well, let's say I is equal to, so let's say E is 200 GPA, I is 500. 5 times 10 exponent 6 squared. All right. So since I want everything to be in kilonewtons, or sorry, meters and newtons, my EI here will be quite an interesting number. 200 times 10 exponent 6. So it becomes, let me just put that into this 200. 10 exponent 6 into brackets, kilonewtons per meter squared times 5 times 10 exponent minus 6. This is 4 millimeter 4, right? So in the end, it becomes 200 times 1, 5. Yeah, it becomes 1,000. So EI is 1,000. All right. So what this will do is that I'll end up with 0 equals to 5 over 3 EI theta B plus EI theta C plus, so here our EI is 1,000 becomes 1,000 times 0.04. Hopefully everything is correct. So this becomes 40 plus 105. Okay. Then here 0 is equal to EI 2 theta C plus EI theta B plus, in this case, we get what? 45 plus 15. Okay. So solving these two simultaneously means that just go to your calculator, you go to equations, and then you choose, I think, the first term. So you have to know what your A, B, and C are. So pretty much in a table form, this is my A, B, and C, just so that we have an idea of what we are doing. So this is for equation 5. This is for equation 6. For equation 5, our A is 5 over 3. Our B is 1. and our C would be minus 40 plus 105. So that'll be equal to minus 145. Okay, for C. Therefore, equation 6, our A will be 2. Our B would also be, sorry, A will be 1. So this is for EI theta B. This is for EI theta C. Okay. So take a note. This will be 2 over here. Oops. This will be 2. And this will be what? Minus into bracket 45 plus 15. So this will give us 60 minus 60. So let's see. So A is 5 over 3. B is 1. C is minus 145. And then A again is 1. B is 2. And then this is minus 60. Let's see what we get. Okay. So what this means is that once you solve them simultaneously, your EI theta B will be minus 690 over 7. And then EI theta C will be equal to 135 over 7. Okay. So you can put, so once you have these answers, you can say that substitute the above into equations 1 to 4. Okay, so let's see if we are on the right path. So for equation 1, it would be for equations 1, it's going to be, let's try to see if I could quickly copy it. That'll be MAB. No. Okay. So this is what we had for equation 1 initially. So I'm just going to delete this guy. Okay, great. It works. Oops, what am I doing? Okay. So I don't need this guy here. Let me just take you off. So we know EI theta B already. So this is going to be minus 690. 690 or 670. 690 over 7 times 1 over 3 minus this. Our EI was already 1,000. So we know that already. So it becomes 0.005 times 1,000. That is 5. So minus 5 minus 120. And now give us minus 125. We end up with roughly so we end up with minus 157 point, let's say 86 kilonewton meter, and that makes sense. And now we try with the MBA. So with MBA, we already know what MBA is. So again, we just copy our information and then we just work with it. Um, all right, so this is our MBA. So this is will be equal to 2 over 3 into brackets minus 690 over 7 minus 5 plus 120. All right, so it's something very similar to what we had earlier, but then the values will change slightly. Instead of 125, it becomes 115. And then we get used to be equal to 49.29 kilonewton meter. The MBC should be the same but opposite to MBA. Let's confirm. Okay. So let's find out MBC. It should be equal and opposite to MBA. To do that, okay. So this then will be equal to, let's see, 2 over minus 6, 90 over 7 plus 137 over 7 plus I think 1000 times 0.045 give us 45. So 45 minus 15. And let's see what we will get with. So 45 minus 15 is 30. Then plus 135 over 7. And we should get, oh, something is not right with my answer. Okay. Let me try to figure out what I did wrong. Second. Okay, so I think I made a mistake. Let me just correct it right here. When adding these two terms, it's 2 over 3 plus 2, so that'll give me 8, not 5. So this was be 8, sorry. Okay, so 8 over 3. So that'll make the first term here also 8 over 3. So when you do the calculations or the simultaneous equations, this becomes 3 minus 690 over 13, not 7. And then this becomes minus 45 over 13. Okay, so let's correct a few things here. So minus, so let's see, what will this give us? Minus 690 over 13 times 3, then minus 125, right? That's going to be a huge value. Minus 125. That'll give us 142. Okay, no, as huge as before. So great. So minus 142 point, let's say it's 7 kilonewton meter. So here, so over 13. So this will give us I think it will get 79.62. And let me correct this one. So this is 13 here. This is minus 45 over 13. And this will give us minus 79.62. Right. Great. So This makes sense because when you sum them up, you should get 0. All right. And then MCB, MCB should be 0, but let's confirm if we are doing the right thing or otherwise. So MCB, so this is our equation for MCB, all right? Let me just copy that here. Okay. So with MCB, let's see. So this should be equal to EI, sorry, 2 into bracket minus 45 over 13 plus minus 690 over 13 plus 60. So let's see if this is going to give us 0. It should anyways, but let's just confirm. If it doesn't, it means that whatever we're doing was not correct. That's what it means, all right? So 60, and this gives us 0. Okay, so it means that our moments are correct. So we found the end moment. And from here on out, whatever we'll be doing is similar to the 3 moments equation method. All right, so now we go to our beam. Oops. Okay, great. So we go to our beam. So this is A, B, and C. So we have these end moments. Let me just exaggerate. So this is our MAB, MBA, MBC, and MCB. Okay, and these are the answers. This is 0. Okay, and this one we got minus 142.7, and here we got 79.62, and here we got minus 79.62. So these are the moments, all right? And once we have the moment, our next step is to find the support reactions, right? So what do? We break your spans into two. I mean, we break the entire beam into separate spans. So we deal with we go with span AB. So we span AB. This is span. I can't even draw straight lines. Interesting. So let's say you're dealing with span AB for now. So span AB. So this is fixed, right? And this is what a ruler. Okay. But what makes this one interesting is that there's an end moment over here, which is 79.62. And even though this end is fixed, we already know what the moment at that point will be. Okay. So it means that we have at least found one of the reactions already. So we need to find our VA and then our VB. Let me call this one VB1. We also have our UDL on it, which I think is given to us as is it 40 kilonewtons per meter? Oops. Yeah, so 40 kilonewtons per meter. All right. So summing of moment at B equals 0. So we have what VA times 6 meters minus 40 times 6 times 3, no 4. Yeah. So then we have so let me say plus MAB plus MBA equals 0. It's always good when we write it this way with the actual variables so that we see what is happening. The reason is because this is clockwise, this is counterclockwise, clockwise, this is clockwise. Okay. So we get 6VA minus 40 times 6 times 3 will give us 720. So minus 720 plus, but MAB is negative, so it becomes minus 142.7 plus 79.62. All right, yeah. So means that here our VA will be equal to 783.08 over 6. Okay, so this will give us 130.41.51. All right, that's fine. Our 130 is fine. Kilonewtons. So our VB, oops, our VB1 will be equal to VA minus 40 times 6. Okay. So this will give us 109.5 kilonewtons. Okay. So whatever we do for so now this is for span. So let me call this one span. Oops. Span AB. Now let me just do on the right. Span BC so that everything looks side by side, easy to solve. Right. So span BC, we also have these moments and these moments. So this is our MCB. This is 0, and this is minus 79.62, I believe. And then we have a point load right here, which was, I think, 60 kilonewtons. Great. All right. Then the length difference here is 1 meter, 1 meter, okay? And we want to find VB2 and then VC, all right? So again, summation of moment at C equals 0. So we have 4 VB2 minus 60 times 1 plus, let me call it this MBC plus MCB equals 0, right? Okay. So here becomes 4 VB2 minus 60. MBC is minus 79.62. All right. And then MCB is 0 anyway. So that goes to 0. Now let's find our values. So 60 plus. So we end up with VB2 being equal to 139.62 over not 4. Sorry, it's supposed to be 2 meters, not 4. Oops, if I delete it. Okay, take your time. Okay, great. So let me do the correction. This is 2 over 2, all right, not over 4, sorry. So divided by 2, and this will give us 69.81 kilonewtons. All right. So now let's find VC. So VC will be equal to 69.81 minus 60, and that will give us minus 9.81, which means that VC is actually a downward reaction, sort of an upward reaction. Okay. So once we have this, we can easily draw our shear force diagrams and bending moment diagrams. And these at this point it becomes so for the shear force diagrams, I don't know what is happening. My things are. For the shear force diagrams, this is very strange. My writings are jumping all by themselves. Let me try it again. Okay. Stranger things happening today. Okay, it's not jumping again. Great. So let's look at the shear force diagram. Okay. So shear force diagram for this particular structure. Again, let me just bring you here. Right, at this point, I'm to assume that we know how to draw these things already, so I'm just gonna so the shear force diagram, it goes up. V is 130, so it goes up by 130, and it comes down by 109. So this is 109.5. This is 130.5. And then this is your shear force diagram. And with this guy here, it goes up by 69.81. And then this is how it looks like. Okay, so this is 9.81. So we can combine the two to give us the general shear force diagram look. Okay, so if you combine both, you end up with an interestingly nice system. Okay. So you have here being your oops, just gonna so we have something like this. Maybe this is my B. Okay, then maybe something like that. So let me make sense of what I'm doing. The shepherd's diagrams are typically much more straightforward to draw, I believe, as compared to the bending moment. Mhm. So this will be the combined version of it, all right, which works. So these are the values. Let me put them there. 130.5, 109.5, 69.8. This is 9.81. Okay, so this is your shear force diagram. Now let's look at the bending moment. For the bending moments, again, we can look at it as separate entities and then we join them together. Okay, so with our bending moment diagram, I can just redraw the parts that we need to use. What happens to these things sometimes? Okay, all right. So let's look at what we had. We had in the beginning a negative value here. Oops. And that was 142. 142. Then we also had another negative value here. I mean, because it's they're all hogging anyways. So here we had 79.62 over here. So typically this diagram here I just drew is a bending moment diagram only due to the end moment. But because there's a UD on it, sometimes the easiest way is to find the UD as WL squared over 8. So it's 40 times 6 squared over 8. And then you draw that in between. So that's going to be somewhere here. Okay. So pretty much this entire height here, this entire height will be the WL squared over 8, which is supposed to be 180. Okay. So that if you want to know this, if you want to know the smaller height, then we need to first find this, and then if you find this height, let me call this maybe, if you find y1, then you can determine y2, right? So pretty much y1 plus y2 is what is given as the 180. And how do you find y1? Y1 is easy to find. You can use the 142, is 142.7. 142.7 and then the 79.62 to determine what the value would be at this end. All right. So that if you can determine the value of this end, which would be your y1 value, you can easily find the y2. Okay. And the easiest way is to use similar triangles. All right. Here, because it's a midpoint, add 142.7 to 79.62 and divide by 2. Okay. So this will give roughly, here will be 111.16. Okay. So if you subtract 180 from that, it means that this your height here will be 68.84 estimatedly. All right. The same approach is also used over here. Again, in this space, you have your 79.62. Okay. But this is a straight line. This goes to 0. Oops, okay. Oops, I don't want that. Okay. This goes to 0 because the moment at that point is 0. So again, because there's a punch load here, you have PL. So this height here, or this entire height in this space is PL over 4. Right? P is 60, so 60 times 2 over 4. So that is 30. So this entire height is what? So let me just make sure that this looks bigger. 70, oops. 79.62. All right. So this entire height, you can easily determine it. Determine that. So again, just like how we had that with the first case, this is your y2, this is your y1. So y1 plus y2 will give us the 30. All right. So let's find out our y1, right? I mean, y1 in this case would be 79.62 over 2. All right, so 79.62 over 2. That'll give me 39. Okay. So what does this mean? Oh, maybe I didn't get my P. My P is what? Yeah, P is 60, so 60 times 2. So it means that 30, oops, I'm hoping I did the correct thing. 30 minus, so like this place will be 9.81, which should be somewhere here because it's negative. So if it's negative, it means that my diagram here will change slightly. It's a bit strange. I think something's wrong somewhere. I'll try and figure it out, but then something is just not right somewhere. Try to think through what could have been a problem. Um, let me just check it again. All right, so let's assume I'm correct. I think everything should check out. Let's assume I'm correct. What this means is that this entire thing here will now look like that. Okay, so it would look, take the shape. Right, so we have that's coming here. This is 0. So we end up with some straight line this way, and then slightly more straight line. So this is your 79.62. This is your minus 9 point. What do we get? We had so 79.62 divided by 2 give us 39.81. So this is 9.81. Okay, great. So if we are to combine the two, let me just continue with my ruler. We have to combine the two. Your Benjamin diagram takes the shape. Yeah. Let's see how it goes. We have this here. So it goes, let me just draw with a red pen. Okay. So it goes somewhere like this. Then it comes down. Okay, then it takes the sharp. So here is a 142.7. This is about 68.84. This is 79.62. This is 9.81. So this is a positive side, negative face. All right. So this is the Penny moment diagram for the combined section. Okay. Um, all right. All right. So this is the solution that we have. Let's look at some specialized cases when it comes to the slope deflection method. Okay. So normally when we solve when we go with the slope deflection equations, we typically assume that the ends are fixed. All right. So we usually assume that the ends are fixed. All right. So what that gives us is which means that we need to derive equations for the equations for what's the name that the different sorry. Okay, so derive equations for the different supports. So typically we assume that um so for the support we assume that there will be these end moments that we need to find, all right? Even if the ends are pin or it doesn't matter which support system we have, we create the impression that we need to find these end supports, all right? But then there are certain cases, as we've seen with the previous example, that um you do have so you do have the ends. So you do have one or two ends being simply supported, right? So we have this end here, which is not simple, sorry, which has a pin support or a hinge support, right? So we can't take advantage of that, all right, whereby one end has a pin support and then use that information to derive a modified version of the slope deflection equation. And what this modified version does that it simplifies the process. Okay. Um, so basically the where the end span is supported uh, by a pin or a roller, let's say at its far end, all right? Um, we can rewrite the equation to take advantage of that, all right? So let's take, for example, the structure here. Okay, so we have to find these moments. So let's say MBA and then MAB. There's some type of loading on it, all of that loading, some deflection that can also occur, like maybe um the support move so that in the end you have this as your new B. So this is delta, this is B, this is B, maybe B prime, this is A, also with the different types of loads that we can have on the structure. So just like the general equation that we had earlier, okay, we know that MAB in this case is 2EI over L 2 theta A plus theta B minus 3 psi plus the fixed end moment AB. Okay. We also do have that MBA is 2EI over L 2 theta B plus theta A minus 3 psi plus the fixed end moments at BA. Okay. But when we have one end, okay, where one end is pinned, it means that the moment at a pin or a roller end support is 0. Okay, so that much we have. So which means that in this case, we can equate MBA to be equal to 0. Okay. Now, when we equate MBA to 0, we can do some few changes in there. So let's say, let's solve for theta B. All right. So pretty much it means that if I'm to expand, I would have what? 4EI theta B over L plus 2EI theta A over L plus 6EI over L psi plus the fixed end moment BA being equal to 0. All right, great. So now let's make theta be the subject. So let's divide through, or let's say that, okay, for EI, theta B over L will be equal to minus 2I theta A over L. Please, this is negative, sorry. We become plus 6EI over L psi, then minus the fixed end moment, BA. Okay. So if that is the case, let's divide through. So let's say divide through by 4EI over L. Okay. If we do that, that means that theta B, oops, change the eraser, strokes, okay. So theta B will be equal to, so if you divide through by 4EI over L, dividing through by 4EI over L the same as multiplying through by L over 4EI, all right? So I'll end up with negative theta A over L plus 3 over 2 psi, then minus L over 4EI times the fixed end moment BA. Okay. So let's just name the equations just for, so this is your equation 1, this is your equation 2, now you have equation 3. So what we can do is that we can substitute equation 3 into equation 1. All right. So let's say substitute equation 3 into 1. All right. And then what that will do is that our MAB, right? If I'm to expand, and that wherever I see theta B, I put this long equation in there, all right? So I get 2EI over L, let's say 4EI theta A plus let me just make sure that I have the right calculations done. Minus theta over L plus 3 over 2 psi. Okay. All right, so we're good. So for EI theta A, so I'm just trying to expand the equation 1 first. All right. So theta B will come in there. And then, so let me do this way. Instead of first writing the theta B, let me write the psi. My eraser is not working. Okay. Okay, so let's rewrite this further. Minus 6EI psi over L. Then plus the fixed end moment, AB. And then, oops. Then plus 2EI over L theta B. Right. So whenever we see theta B, we can put in the equation 3. So we can have into bracket minus theta A over L plus 3 psi over 2, then minus L over 4 EI. FEM becomes a quite longer thing that we're doing, but in the end, it will but simplified anyways, all right? So if we are to simplify that, our MAB will be equal to, let's put there, so it becomes 4EI over L theta A minus, am I correct? Yeah, so this is over 2, not over, yeah, sorry, see? Yeah, here's 2, this is 2, sorry. This is 2. All right, so it becomes EI theta A over L. Then we have here minus 6EI psi over L. Then again, we have plus 6EI psi over 2L. Then plus the fixed end moment, AB. Then minus, what do I get here? So I get fixed end moment, BA, think over 2, right? Hopefully what I'm doing makes sense. Hopefully, yeah, it should. Okay, so it means our MAB will be equal to, here I'll get 3 EI over L theta A minus so negative 1 plus I mean 6 plus 3, so it becomes what? So I get negative 3 EI over L psi. Then let me put these guys into brackets because they are important. Oops. So the fixed moment FMB and then BA over 2. Okay. So here I can find here FMAB. Let's bring the 3EI over L out so that we have theta A minus psi. All right. Then plus, so this equation here can be written in an interesting format. Okay. So here we are assuming that the fixed moment at AB and then half the fixed, this is V minus, and half the fixed end moment at BA. But if you have a pin support, okay, because a pin supports the moment is 0, what it simply means that if you have any load on the structure, right, and then you want to find the end moment. So if you want to find the end moment, only let me call this one AB, only MAB will have an end moment. BA, or the end moment, no, so let me rather make it FEMAB. So the end moment or the fixed end moment FEMAB will be there, but then the fixed end moment BA will not, or will be equal to 0. All right. So if you take a look at it, this differs slightly from what we've had in terms of fixed end moment. So I'm just going to copy something for us to see. Yeah, okay. Just a second. Okay. So it should appear shortly. Okay. So what And it, or what the general slope deflection equation does is that it's assumed that both ends are fixed. That has already been explained, but that we are trying to modify it and take into consideration the fact that we have a pinch support. Okay. So if that is the case, what this means is that then we'll use the modified. So this becomes the modified fixed end moment. Fixed end moment. Okay. So this is taking into consideration the fact that one end is actually pinned. Okay. So once one end is pinned, what this means is that I can actually have so that means that the fixed end moment BA will be equal to 0, but then the fixed end moment AB would be there. Okay. But this is a modified fixed end moment. It is not the same as the one we had previously. So please take note of it. So there's a modified fixed end moment. Okay. So that modified fixed end moment here, if we had a case whereby it was a UDL that was on the beam, then that modified fixed end moment would have been WL squared over 8. Okay. So I can rewrite this equation into a more general form that MRH is equal to 3AI over L theta R minus psi plus the fixed end moment RH, where the R stands for the rigid end and then the H stands for the hinge or pin support. Okay. So the rigid end means that has a fixed end. Okay, just so that we know. Or fixed support. All right. And this becomes like a modified version of the slope deflection equation. All right. And let's see how it works. Okay. We had an earlier example that I solved. So I'll just go with the same approach and then let's see how everything works out. So we have this example and that we solved, I think, not too long ago. So I'm just going to solve the same example. Should appear. So there's an example for us to look at. All right, so nothing really is different from what we had, okay? Just that now we know that this end here is pinned, okay? So we will use the modified approach for that. Okay. So using the modified, which would be the taking into consideration the pin jointed end. Into consideration, what this gives us is that when calculating our fixed end moment, things will change slightly, all right? For span AB, nothing changes, right? So our fixed end moment for span AB remains the same because support A is fixed, and since support B is an internal support, it behaves as though it's also fixed, right? So you can use that analogy here. Then we have our UDL. We can easily determine the fixed end moment. So basically the same thing as we had earlier. So I'm just going to copy that part. That nothing really changes over here. So we have this for the fixed end moment. So just going to bring the same thing here. Nothing changes. Then when it comes to the one with the what's the name? So if we come to span BC, so we span BC, So span BC, we now have this, right? So this is again B, our C is a pin support, then we have the point load. So I actually brought the wrong uh, diagram. So we have the point load, which I think is 40 kilonewtons. And we have this length here, 1 meter, 1 meter. Okay. So what is going to happen is we'll go to our fixed what's the name? Fixed end moment table. Then look for one that corresponds to the modified version. So typically on the fixed end moment table is the one on the right. Okay. So let's show that quickly. Should appear any moment from now, I believe. Yeah. Okay, so this is what we have, which means that the fixed end moment, we only look at FEMAB. Okay. We don't do BA. No B in this case, only AB. But this AB is the modified version. Okay. So this then becomes what? 3, our P is 40, our L is 2 over 16. Okay. I'm hoping P is actually 40. Let me just go back and check. So you see P is 60, not 40. All right, so P is 60. Good that I checked. Okay. So P is 60. All right. So this is equal to 3 times 60 times 2 divided by 16. And that will give us 22.5 kilonewton meter. Okay. So please, this is modified. I always just want to use the word modified so we see that it is not a typical fixed moment where it is actually PL over 8, PL over 8, as we had in the first problem. All right. So what I'm trying to do is I'm trying to solve the same problem using two slightly different approaches. One, assuming that all the ends are fixed and go by the general approach. And then the second method is pretty much the second example, is to look at the fact that one end is actually pinned and taking advantage of that to make our calculations less strict or more easier to solve. Let's put it that way. Okay. So let's write the equations now. Okay. So our MAB, MBA will be the same story. Nothing's going to change on those ones. Because I mean it's fixed regardless of where we are. So let me put those ones down somewhere. Just gonna copy and paste. All right. Same thing that I'm working on. I don't need to rewrite the whole thing. So forgive me if I'm trying to be lazy, but that is fine. Okay. So these are what we have. MAB, MBA. Now, when it comes to MBC, even with, okay, let me just write that one out. So MBC, because we are taking advantage of the fact that one end is pinned, our equation, so what we are using is that what MNF is equal to 2EI over L 2 theta N plus theta F minus 3 psi plus the fixed end moments, right? So this is the general equation that we are used to. So this worked for this, the general equation, it worked for these two guys over here because, oops, because both ends are fixed, right? So here we assume that both ends are fixed or they have moments or the moments at those ends are not zero, right? Now we are using this new approach. MRH is equal to 3EI over L theta r minus 3 psi, I believe, plus the modified moment. Okay. So what this means is that your MRH has a value, but your MHR is 0. Okay, we'll look at this. No stress. So what we are focusing on is to work with the MRH. Let me change the color. So work with the MRH option for span BC, right? So for span BC, we have MBC 2E, the L is 2 meters, I believe. Then theta B minus 3 psi, where our psi, I think from the previous calculations, it was trying to look for it. Just give me a second. So it became 3 into bracket minus 0.003. I think there is 0.3, not 0.0, because of the fact that this is negative downward deflection on the left is negative, all right, for that particular span. Plus here, our fixed end moment will be the modified one, so the 22.5. And since it is counterclockwise, it becomes minus 22.5. Okay. Our MCB is 0 because now we are saying 0, so there's no need to put any equations there, right? We don't have to at this point. Okay. So what we need to do is to now come in write our equilibrium equations. So we do have so MBA plus MBC equals 0. All right. We already know what our MB is, so I'm just going to copy that. I don't need to rewrite everything. So this is our MBA. Let's see, does it did it copy? Okay, we'll give it a try and see. Okay, so everything copied. Almost. Let me just take some of the values away. Okay. So this is your MBA plus, so let me expand MBC. So I get EI theta B minus what? I think we had so it becomes plus 0.045, I believe. Yeah. Then minus 22.5. So all of this is equal to 0. Let's see if this is solvable. I left out something, sorry. Let me correct it. Oh, sorry, not 2. This is 3. Oops. Please take note, this is 3 because this is a modified version. So this is 3, not 2. Very, very important. Otherwise, everything becomes all over the place. It's so easy to mess this thing up sometimes. So 3EI, theta B is actually the better or the correct answer, right? 3 over 2 times 2. So this will give me times 0.03. This will give me EI 0.09 minus 22.5. All right. So let's try to summarize stuff. All right. 2 divided by 3 plus 3 divided by 2 should give us what? 13 over 6. So we have 13 over 6 EI theta B. And then EI, I think we had EI to be equal to 1,000 from the previous calculations. So 1,000 times 0.00, 1,000 times 0.005 will give me 5, right? So here's 5 minus 5 plus 120, and then 1000 times 0.09 should give me 90, I believe. So it becomes plus 90 minus 22.5. And then that will give me so then here we can do the math. All right. So let's see what this will give us. Hopefully, we get the right answer. So minus 5 plus 120 plus 90 minus 22.5. That will give us, so it means that 0 is equal to 13 EI theta B over 6 plus 182.5. This means that what? EI theta B is equal to minus 182.5 times 6 over 13, right? So so this will give us 1-1095 over 13. So this is your EI theta B, right? It will not give you the same answer as the previous one. In the previous we got 690 over 13 minus 690 over 13 anyways. So let's see if we are correct, okay? Let's find out MAB. So here our MAB, let's try to rewrite it. So MAB will be EI, so EI theta B will end up with minus 1095 over 13 times 3, hopefully, minus 5 minus 120. So let's see if what we have makes sense. The answer should be the same as what we had previously. And it's not. I don't know. Maybe I had made some mistake somewhere, trying to figure out what the mistake could be. Because I'm doing these calculations in real time, it's possible that I might have missed something, right? So let's just cross check and see. All right, so I think I found my mistake, right? So please take notes. It's not 3 psi. I mean, the equation here is supposed to just be psi, not 3 psi. All right, so let me just correct it. Please take notes. I think that's where the mistake is coming from. So it is psi. Yes, I have to come back here and then get rid of this guy. The 3 in front here. All right, it's not needed. Great. So it would affect this here. Let me just correct it. So it becomes 3 times 0.03 divided by 4, and then that'll give me 0. So this is actually 0.0225 minus 22.5. All right. So let's solve that. So this will be 22.5. Okay. So if that is the case, then these two cancel out. I'll get 115 over here. So this becomes minus 115 times 6 over 13. Let's see if this makes sense. Minus 115 times 6 divided by 13. That'll give me, yeah, great. So I got the right answer. So this will give me minus 690 over 13, right? So minus 690 over 13 times 3 will give me, I think, minus 142.7 kilonewton meter. So that's for the MAB. Now let's try MBA. MBA would also be going back. MBA will be 2 over 3 minus 690 over 13, then minus 5 plus 120. All right, so that will give us what? So plus, what's the name? 115, I believe. So that will give us 79.61 or 62, right? It's just like what we had earlier. So let me just correct it. 79.62 kilonewton meter. All right. So what it's going to do is that our MCB, right? Our MCB, which is, no, not our MBC, because our MCB is 0 anyway. So our MBC, rather, MBC will be equal to, our MBC was what, 3EI, so it becomes 3 over 2 minus 690 over 13 plus 22.5 minus 22.5, and this should give us minus 79.62 kilonewton meter. And then obviously our MCB was 0 from the onset. All right. So you will see that with these sets of equations, with these sets of equations, pretty much finding the reaction. So finding reactions and drawing shear force diagram and bending moment diagram is as in previous example. All right. All right. Okay. So these are for typically beams, right? So what we've been looking at have been beams. There are a few things to take a note of. The fact that this same question that we solve can be solved in two different ways, right? So option one is to assume that both all ends are fixed. So whether it has a pin end support or whatever, you assume that that end is fixed, and then you solve it using the general equations as they were originally given. But what happens is that your computations are longer. I mean, you spend more time with the computations, right? So if one end is pinned, you might want to take advantage of that and then use that to solve your problems. Okay. So there are quite a number of examples. I'll try and send as many as I can to you guys if when I find them. But the idea is that this is like one of the most basic approach in trying to analyze these types of questions. Now let's look at how to analyze frames. All right. So we've done beams. Now let's look at frames. So let's say analysis of frames. All right. Frames typically have a vertical component to it. So you usually have the horizontal member and then some vertical member, right? So this could be a frame. This could be frame. All right. Or you could even have frames that look like this. So you could have different types and kinds of frames, all right, in terms of the arrangement of um, the different members with their corresponding joints, all right. So here we have, oops, okay, let me just change a few things for some of them. You can have a pin, it's fine, right? It's not always going to be fixed. So that is A, B, C, and D. Again, A, B, B, C, D, and E. A, B, C, D. All right. There are two main types of frames. Two types of frames. So we are looking at frames with sway. We'll explain what that is. And then frames without sway. When we apply a load to a frame system, and then there is side movement, I will explain shortly. There is a side movement of the ends of a column or columns, can be one column or columns. We call that, so there's when there's a side movement of the ends of a column in a frame, we call that movement sway. So for example, let's say if I have um, this frame here and apply maybe some horizontal load to it, if the frame shifts, right, it shifts this way, okay, so the supports remain in position, but then the top portion of the column shifts, or where there is some rotation of the column with respect to a fixed point, then we say that sway has occurred. All right. So here's an example of a sway, and some structures typically have sway even when properly designed. All right. So we need to take into consideration analysis of such structures and then understand how we can calculate the reactions. Okay. Now, well, it's not all structures that when you apply some loads to it, they tend to have that side movement. Okay. And we'll look at the two, the sway and the no sway. All right. So let's start with the non-sway, since we've spoken a little bit about the sway. So non-sway frames. Okay. So as the name implies, no side movement of the columns. Okay, columns and beams. So let's add that to it as well. Okay. So usually, how then do we have a frame that would not side sway? Okay. Okay, so let's see. Um, if you have a frame, all right, and then we restrain. So when we restrain or into bracket prevent um the frame from moving, right? So that's also one way to look at how to not have a sway system. So an example is this. So going back to the frame up there, okay, I can decide to add an additional frame, okay, and place the support on it. What the support, let me just label it A, B, C, E, and E. The support at E effectively restrains the frame from swaying. Okay, so let's take note of that. So it means that even if you apply whatever load over there, because of the pin support, it could be a pin, it could be a fixed support. It's one of the two. If it's a roller, there'll be sway, right? Well, again, it also depends on the orientation of the roller, but then typically a pin support and then a fixed support at joint E will prevent any form of sway. So that's one way to look at sway. I mean, to have a non-sway. Then in some cases also, let's say we have an unrestrained let me just put when we restrain the frame. Sorry, let me just go back and complete the statement. Right, so that's so now back to the what I was typing. When we have an unrestrained frame, but so there's a big but the loading on the frame is symmetric. So one, the loading is symmetric. The geometry of the frame is also symmetric. Okay, so both the loading and the geometry are symmetric. When that happens, then we can have a non-sway frame. Okay, so here is an example. I have this frame here. If I place a load right at the midpoint, okay, so that this length here, L1, the same as this length here, L1, the load is right at the midpoint. Maybe let me call this one L over 2, L over 2. This is perfectly symmetrical. All right. So it's symmetrical both in the load because the load is right at the center, dead at the center, and also the frame is symmetrical in the sense that if you cut it along where the load is being applied, you get a mirror image of it, one on the left and one on the right. So such a frame will not sway because of the fact that what's the name? The symmetry of both the load and then the frame. Another example would be if you have this as your frame, okay, and then you have maybe some loads at this end. So these are two loads. The distance between the load to one end is A, another end is A. The loads have a magnitude each of P, right? And then the lengths of the frames are about the same. Again, if you cut a section through the midpoint, right, this way, it is symmetrical. Again, this will be a non-sway frame. I'm giving more examples so that we can be able to tell if a frame will sway or otherwise. Now, the last example, you have this here. Apply a load W and a load W on this end. Because the loads are moving opposite direction and they are both at the same location along the legs of the frame, again, this frame will not sway. All right. So this way is because of what the geometry and the loading of the frames is both. If one is symmetric and the other is not, the frame will sway. So let's look at some exceptions. Okay, let me put it that way. So you're going back to the frame up here, right? The frame is perfect, but you have your load somewhere here. All right. So definitely, if this is the midpoint of it, this particular frame is no longer symmetric because it's not, even though it is symmetry in the geometry, it is not symmetric in the loading. So here, this will undergo sway. Okay. So you have it. If I'm to draw the deflected shape, it would look something like this. So then the frame will just go this way. This guys, what's going to happen is that the deflected shape will look something like this. Depends. Maybe let me just, it's going to expand outside rather. All right. So you can see that the joints, the joints are not moving. So let's say this joint, joint A, B, C, and D are not moving. But in this case, joint A, B, C, and D, B and C have moved. Now we have B prime somewhere here, and we have C prime somewhere. So there's been some change in the position of the joints, which means that sway has occurred. Okay. So here's an exception of where, I mean, just to show us that this is when we have sway occurring. Otherwise, the other three that we just looked at all will not have sway, or sway is prevented from occurring. All right. So we have two main ways by which sway can be prevented. One is if we provide some restraints, right? So usually restraint can be the support system. And mostly it's we provide that restraint at the beam level. Okay. Let me add that. The beam level. Okay. What else do I need? Yeah. So this is just to explain to us sway and non-sway. So again, when there's sway, it means that there would be some unknown displacement delta, which we would need to find, right? And then because there's sway, it also means that we would have the chord phi. There'll be a chord here to phi. So let me phi 1 and phi 2. All right. There are some instances, I think let me just label all of these for us so that it's easier to reference them going forward. Okay, I think I will talk about that later rather. Let me just talk about it later. All right. So usually when there's no sway, it means that the psi, when there is no, the psi is 0. All right, regardless of it's 0. And the analysis of non-sway frames. Okay. This is similar to the analysis of beams. So the two examples that we've looked at so far are enough to help us to analyze frames that will not sway, right? The only thing is that we need to understand that the fact that you can have more than two members connected to a joint. Let's see if we can find an example to look at. So there's an example in the Hibla, I think example 11.6. So I'm just going to talk about it using example 11. Oops. 11.6 from the Hibla. Hopefully I got the spelling right. I'll say Hibla, I mean. So they have a more, should I say, elaborate example. I'll try and see if we can get that one done. I'll jump a few steps because everything looks the same with respect to the analysis of beams. Okay. So we do have something like this. Hopefully. Okay, so this is pinned. This is fixed. This is also pinned. Okay, so we'll take advantage of the modified equation. So we have these as our loads. Prefer to use this guy here. Okay, great. So this is 50 kilonewton per meter. And then here we have 30 kilonewtons. Let's look at the dimensions. This is 4.5. And these lengths are, let me see. This is 2.4, 2.4, and then 3.6. If I is equal to 8 times 10, the 80 times 10 exponent 6, millimeter 4, E is giving us 200 GPa. here will be I. This will be 2I. 4I. And then this one will be this will be 3.25I. Okay. Hopefully, I think I'm correct. All right, so let's see. I mean, the key thing is identifying your what's the name? Your DOFs. All right. Um, so let me label them so that at least we have this is A, I believe, B, C, D, and E. So here, because the support at A is provided, so there's some restraint, or as a fully restrained against sway. Okay, so in this case, there will be no sway. So sorry, this case there won't be any sway. So this is a non-sway situation. Okay. Our DOFs would be our DOFs would be theta B, theta C, theta D, and theta E. I'm hoping I got all my information right. Let's see if I'm correct. There's theta B, theta C, all right. Yeah, theta B, theta C, yeah, and theta E and D, all right. So these are the unknowns, 1, 2, 3, 4. I'm going to use the modified approach to make my analysis a bit more, easier for me, all right. So let's start. So let's write the equations for all of them. That's going to take a while. I'll try and write as many as I can, right? So MAB will be equal to 2E 2I. All right. The L is what? 4.5. Then please take note that theta A is equal to 0. All right. And then delta is 0 or psi is 0 for all cases because there's no settlement and there's no sway. All right. So this would reduce to theta B. All right. What I should have done first was to have found the fixed end moment. So let me just do that. Oops. What's wrong with my mouse? Let me bring you here. So the fixed end moment Okay, so here we are. Put it back into black. Okay, so our fixed end moment, let me just put that here. Fixed end moment, AB will be equal to fixed end moment, BA, and it's 0 because there's no load on member AB. All right. For member BC, our fixed end moment at member B, C, the same as the fixed end moment at member CB, and that will be PL over 8. So that will give us 30 times 4.8 over 8. Okay, so 30 times 4.8 divided by 8. This will give us 18 kilonewton meter. Then the fixed end moment at CB. All right, so this here is a modified approach. So from the fixed end table, that would be WL squared over 8. So this would be 50 times 3.6 squared over 8. So 50 times 3.6 squared divided by 8. That will give us 81 kilonewton meter. All right. The fixed end moment in for CD will be 0 because there's no load on CD. All right. So please take note this one, no load, no load. The same here too, no load. Okay. Here we are using the modified approach, which is we taking into consideration that the support at sorry, not CB. How am I putting this thing? CE rather. The support at E is 0. So we have AB, BA, great. BC, BCCB, great. Then CE, great. Then CD, also great. Okay. So let's continue with our equations. So this is 0. So this order we have for this end, right? So it will be 4EI over 4.5 theta B. So that's for MAB. Then MBA will be 2E to bracket 2I over 4.5 2 theta B. And that'll give me 8EI over 4.5 theta B. Okay. Now let's look at MCB. So normally I'll show the moments. Okay, this moment. So these are the moments we are looking for. Right. So this is MAB, MBA, MBC, MCB, MCD, MCE. This one will be 0, so we don't even need to show that. Okay. So these are the moments we need to find anyways. Right. We don't know what they are, so we need to find them. So MCB, well, let's do MBC first. So let's do MBC will be equal to 2E over 4I divided by 4.8. Then we have what? 2 theta B plus theta C, and then minus a fixed end moment of 18. All right. So if we are to expand that, this will give us 2 times 4 is what? 8, 8, 16. So it becomes, so we have 16 EI over 4.8 theta EI theta B, sorry. Then plus so we have 8 EI over 4.8 theta C minus 18. All right. So now let's do for MCB. Sorry, Yeah, so MCB will be the next one, and it's 2E 4I over 4.8 2 theta C plus theta B plus 18. So that'll give me 16. Oh, okay. I think I rewrote this too many. Okay. So 16 over 48 EI theta C plus 8 over, not 40, it's 4.8. 4.8 EI theta B plus 18. And we have what? MCE. With MCE, we are using the modified approach, right? So it becomes 3E, where the I is what? 3.25, right? So to bracket 3.25 I, and then the length is what? 3.6. So that'll give me what? Theta C, all right, plus the fixed end moment, which will be minus 81. So this will give me, let's do the math and see what you will get. 3 times 3.25 divided by 3.6. Yeah, that's an interesting number. Okay, I was actually my answer in this form. So 9.75 over 3.6 EI theta C minus 81. Then our last bit, MCD. Yeah. So MCD again is a modified approach. So 3EI over, I think, 4.5 for the height. Theta C. There's no fixed end moment. So this is your answer, 3EI theta C over 4.5. Okay. So just take note that the reason we didn't bring those other two was that put them here. MEC is equal to MDC. They are all 0. Okay. So we didn't bring those over here. So these are your slope deflection equations. All right. So if there's going to be any mistake, this is where the mistake occurs. All right. Where admin stuff can easily go south. So usually I would advise that when we are dealing with this, we spend a bit more time trying to make sure that we get the additions and all of that right in this area. Okay. So let's do the equilibrium equations. So let's look at the joints. Our main interest will be joint B and joint C. So for joint B, MBA plus MBC equals 0. Therefore, in joint C, there are 3 over there. MCB plus MCE plus MCD. All right. So here is a typical example of more than 2 members at a joint. Okay. So you would experience this when you are dealing with the frames. All right. For beams, typically you have only two members at a joint, but for frames, it could be 3, it could be 4, it could be 5. It could be as many as we want. All right. So these are the equilibrium equations, means that we have to add MBA and MBC together. All right. So let's look at the joint B, which is MBA plus MBC equals 0. And this would be, so let's say MBA is what? So it becomes 8EI over 4.5 theta b plus 16 EI over 4.5 theta b plus 8 over 4.5 EI theta c minus 18 equals 0. So let's simplify what we have. All right. I always like to leave my answers in this. So this one becomes 24 over 4.5 EI theta b, then plus 8 over 4.5 EI theta c minus 18 equals 0. You know what? Let's label all our equations. So this is equation 1, 2, 3, 4, 5, and 6. So this is 7. Yeah. So here you will be writing a lot of equations. So that's should I say the downside to the slope deflection method is that you write a lot of equations. Yeah. So that's the only thing that we need to be concerned with. So for joint C, that is MCB plus MCE plus MCD for 0. So let's write that. Okay. And let's see what our MCB is. That is quite long. So our MCB is 16. Oops. So that will be 16 over 4.8 EI theta C plus 8 over 4.8 EI theta B plus 18. Have I missed something? I'm hoping I haven't. Otherwise, I'll be in trouble. Yeah, these things do happen. I think I see where my mistake is coming from. So this is 4.5. Yes. So let me just correct this. It was good I caught it first. Let's put 4.8 and 4.8. So 4.8. So it means that this will change slightly. So 8 divided by 4.5 plus 16 divided by 4.8. That gives me 46 over 9. All right. So 46 over 9 was good. We caught it. So MCB is this plus MCE, and MCE is what? 9.75 over 3.6 EI theta C minus 81. Then plus MCD is what? 3 EI theta C over 4.5. Okay, so let's summarize this as well. And then we have the two equations that we need to solve this problem. Okay, so let's see. The theta b is only 1, so we have 8 over 4.8 EI theta b. The theta c, there are a few of them, so let's sum them up. There's a 16 over 4.8, and then so if you sum all of them up, you get what? 161 over 24 EI theta c. I like to leave my answers in fractions because I don't have to round anything up, and I'm sure that my answer at the end will be the most accurate that I can have. All right. Then we have minus 81 plus 18. So that will give us what? Minus 63 equals 0. So this becomes our equation 8, I believe. Okay. So we have these two equations that we need to look at. Equation 7 and equation 8. Right. So we can say solving equations 7 and 8 simultaneously. Um, so we'll have values for values for EI theta B, and then values for EI theta C. All right. Yeah. So this we can do with our calculators easily. They have to do it from first principle. So for the 6.9 divided by 9 is the first term. Second term was 8 divided by 4.8. The C term will be 18 because it goes to the other side of the equal to sign. Then the equation 8, the first term is what? 8 divided by 4.8, I believe. Then we have 161 divided by 24. Then we have 63. Let's see what we get at the end. Crazy. Yeah, I know. So here we got 0.5. I'm guessing I'm correct. We'll see. And this is 9.27. I'm hoping I'm correct, right? Otherwise, then we've spent so much time to do all these plenty calculations anyways. So let me confirm if I'm on the right path. So let's find MAB, all right? So our MAB, our MAB was what, 4EI? So it was 4EI over 4.5 theta B. So this is going to be 4 over 4.5 times 0.5. Let's see if we are correct. This is where we'll show. So 4 divided by 9, I believe. Yeah, that is correct. So we get 0.44, plenty force, 0.44 kilonewton meter, which is great, right? Then our MBA would be 0.888 kilonewton meter, all right, or 889 or whatever, all right? Then our MBC, so here I'm just inputting the values of C theta, uh, EI theta B and EI theta C into the above equations, okay? So that we can do, okay? So MBC will become minus 0.888 kilonewton meter. We can look at, let me put this here, MCB, just so we see something interesting. MCB is 49.7. MCD, that's 6.18. And MCE is minus 55.9. All right. These were the three that were sharing joint C, right? So if they are sharing joint C, what it means is that if you sum them all up, if you sum, it should be equal to 0. Okay. So that's one way to check. If you sum, so when you take the end moment, the internal end moment at a joint, when you sum them up, they should give you 0. That's how you came up with the equilibrium equations, right? So it means that my 49.7 plus my 6.1318 minus 55.9 should give me 0 or something very close to 0, right? Maybe, yeah. So if you get it and everything is close or 0, then it means that you're on the right path, okay? And please take note, we also had that uh, M EC was equal to MDC, that was 0, all right? So those were also part of whatever we had. So from here onwards, then you have to draw your, so here onwards, we say find reactions. Um, find reactions, and then draw diagrams. Okay, so here we are looking at shear force, axial force, and then bending moment. Let's see how we do this quickly. Or I think I'll just put the answers there. As a form of exercise, we should all try that and see if we can reproduce the same thing. And then you can always get back to me if you have any questions, okay? All right, so I've taken some time to just draw the bending moment diagram, the shear force diagram, and also the reactions, all right? They might slightly be different from what you have done or what you do, all right? So take your time, just go through it, do this part, and then we'll see how things pan out from there, all right? So the bending moment diagram, the shear force diagram, and then the axial force diagram, and also the reactions. Definitely, the reactions are needed first before any of the other diagrams can be drawn. All right. Okay.